Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, so we start again with this chapter number 8. After chapter number 4, we continue with chapter number 8, the association kinetics of the molecular. Okay, so here we will focus on the association of the kinetics. So how fast uh, the association A plus B becoming C, or C becoming A and B again. Okay, and we also will look at the factor that influence their speed. So what are the factor that will influence the speed of the reaction? Okay, so let me start with the biomolecular association. So we have two molecules again, A and B, or protein and ligand becoming a complex. A plus B, here is A plus B becoming C. There is no C becoming A plus B. So this alpha is the rate constant of association. So the rate of losing the A, this concentration, or the protein. Okay, so if we have 100 protein, so after some time, let's say become 50. So the rate, we want to see what are the rate of the losing of the association of protein and the ligand. Okay, so dA over dt equal to minus alpha A B, concentration of A, concentration of B. And if we let the A, concentration of A, and concentration of B equal to the initial concentration minus X, and B not minus X, where X is the amount of A and B consumed in time T. So we are going to get, or if we put back into this equation and rearrange, we are going to get and solve the equation in our textbook. So we are going to get, if the condition where if A not the initial concentration of A is not equal to the initial condition of B, so solving that equation, so we're going to get X equal to A naught B naught exponential minus alpha A naught minus B naught, and so on. Okay, so this equation. Okay, so we are going to get this equation. So we can put the value of A naught B naught into this equation, so we can see the amount of X, or of A and B consumed in time. Okay, but if A naught equal to B naught, so we can see that here A naught minus B naught, A naught minus B naught. Okay, or from the previous equation again, or in our textbook, so we are going to get dx over A naught minus x squared equal to alpha dt. Okay, so if we integrate one, so we get, integrate this one, we have 1 minus A naught minus x equal to alpha t plus c, and setting t equal to 0, x equal to 0, so we can get this equation, the solution for this equation C. So C equal to A over A naught. So putting back in, rearrange this, so we can get x equal to alpha A naught squared T over 1 plus alpha A naught T. Okay, so here we can see that these are the, so if we plot this graph and this graph, you can see the difference of the consumption of the protein and ligand. Okay, so next we see the if these are the C can goes back to A plus B. Okay, so we have beta rate constant. So here we see that these are the concentration near equilibrium. So A equilibrium, B equilibrium, and C equilibrium, and setting X deviation from equilibrium into this equation, and the rate of change for A different from the previous one. So dA over dt equal to minus alpha AB, reducing the C, and plus beta C, where C dissociate becoming A and B again. Okay, so if we put back this equation, okay, this equation into this equation, so we are going to get this equation, the first one. Okay, minus alpha A equilibrium B equilibrium plus beta C equilibrium minus alpha A equilibrium plus B equilibrium plus beta x minus A x squared. Okay, so these are just A x squared plus bx plus C. Okay, so if we set x equal to 0 point, or if x is a small number, let's say 0.001, so we see that x 0.001 times 0.001 become a small number, so we can ignore this, so we're going to get this equation. Okay, so let's say if we have this initial value t equal to 0 equal to x naught, x0 equal to x naught, solving this equation, so the answer will be x equal to x naught exponential minus alpha A equilibrium plus B equilibrium plus beta times t. Okay, so we can find the we can use the A constant, equilibrium constant A and B. Okay, so we can get this one is just the x will be going smaller and smaller. Okay, so here what we can see is that the higher order kinetic process we have an exponential time cost near equilibrium. Okay, so all going to become after t equal to infinity, all become an equilibrium. So in order to A to meet B, okay, so A or B must be diffused in the solvent. Okay, so as long as they did not meet, so there will be no association, so depend on the diffusion, and here it is the diffusion limited association, and this one is uh, yeah, the one that uh, the factor that uh, limit the association. Okay, so here when association depend on the frequency of A and B meet. Okay, so how they meet A and B, so this one is these are, let's say these are the protein and these are the ligand, so the ligand will let's say A is fixed, the protein is fixed, ligand is moving, so let's say the ligand is moving around and meeting the A, so the nearest region that it can meet the A is in this region, the dot region. Okay, so solving this model, okay, so we're going to get the diffusion equation for this model is equal to 1 over r squared partial over partial dr r squared partial cbr over partial r equal to 0. Okay, so these are the concentration. So so we set the concentration for B. So solving the previous equation. So without a boundary condition, so we just uh, integrate twice or integrate uh, once. Okay, so we are going to get CB equal to minus A over R plus B. Okay, solving this, so we're going to get this one. But if we apply the boundary condition where CB A plus B equal to 0, meaning that in this region there will be no concentration of B. So solving it, so we're going to have CBR of equal to minus A plus B CB of infinity over R plus CB infinity. Okay, so we're going to get this equation. Okay, CB, the concentration for B at infinity, there is a concentration. Okay, and these are the limit that it can attach to the protein. Okay, and if we take the flux or the movement of the ligand, okay, into and out from the protein, So we see that the flux of molecule at R equal to A plus B. Okay, so at this one, A plus B, the movement. So it is uh, J equal to minus dB CB infinity over A plus B. So where dB is the diffusion constant for ligand or molecule B. Okay, so the collision frequency is assuming that the protein is a sphere and ligand also a sphere. So the collision frequency is equal to 4 pi A plus B. So the division constant of B and the concentration of B. Okay, so how fast the molecule B meet with the protein A. Okay, so here we can say alpha equal to CB A alpha times CB infinity. So here we can see that alpha is the association rate constant. Alpha equal to 4 pi A plus B d B. Okay, so if we know the radius of A and the radius of B, and if we know the diffusion constant for B, so we can estimate the association rate constant for this reaction. Okay, and if both, because we know that in solvent, protein will move, and the ligand also will move, so we can see that the rate constant equal to 4 pi A plus B, the division constant for A and division constant of B. Okay, so we see this one. So if dA is small and dB is high, so meaning that dB or the ligand can find or can find the protein again and again uh, in time. Okay, and also if we use the Stokes-Einstein relation, so where D division constant equal to RT over 6 pi R eta, and setting R equal to A, the radius equal to A equal to B. Okay, this one is meaning that the radius of the protein and the radius of the ligand is same, so we can get alpha if we put back this D into this this equation, okay, or this equation, so we can get alpha equal to 8 RT over 3 eta. Okay, so meaning that we do not by using this equation or the Stokes-Einstein relation, so we do not need to know the division constant for A, division constant for B. Just play with these are the gas constant, T, the temperature, and also the viscosity of the solvent. Okay, so if we know the temperature, or if we set the temperature and the viscosity of solvent, so we can estimate the rate constant for that association. Okay, and if the molecule, okay, let's say the protein and the ligand has a charge ion, say, so the collision frequency can be written without any proof is this equal to 4 pi dBCB equal to A plus B infinity 1 over R squared exponential UR. Okay, so these are uh, the energy. Okay, the energy UR over KT dR. Okay, so we can uh, 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 sum all the energy. Okay, divide with this 45 dB C. Okay, so we can get this frequency. Okay, so here we can see these are 45, so these are K, T, T, R. Okay, so here you can find the energy UR. Okay, so we can uh, find the denominator, the value for the demo. Okay, and as we know that the protein is large and the ligand is small, so for molecule that only it we only react, or the ligand that only react when key and log site meet. So here we can see that here A is the protein. We have a lot of site here, but this ligand only can react with this site. Okay, or in this case, if we uh, make it as a square, so this site, this ligand can only react with this site or attach with this site. Okay, so the rate association rate or the rate constant is equal to alpha equal to 2 pi s plus b d b. Okay, so these are the radius of the reactive site of the protein. Okay, so we have this equation. Okay, so what we need to know is the dB, or for example, we know from the Einstein relation, alpha equal to 8 RT over T eta. So we get alpha. So we can use this alpha to find the uh, the radius of the reactive site. Okay, and if B must fit in the reactive site of A, then the section rate constant must be alpha equal to 4 pi S minus B D B. Okay, so if S equal to B, it will not fit. Okay, it will not fit. So B must be less than S. Okay, in order to be the ligand to meet or enter the reactive site or the binding site. Okay, so here we can also get alpha equal to 4 pi RT over 3 pi eta. Okay, so here we can get this equation. Okay, alpha equal to, so meaning that we can find the association rate constant using this equation. The T, temperature, again the temperature, and the viscosity of the solvent. Okay, and these are the last one. So protein ligand association. So many protein bind their preferred ligand very rapidly. So these are the association rate constant that we can get from this. These are A and these are B, and these are the uh, association rate that produce the C. Okay, and if B and B A, the ligand then can move freely in solvent, will do the association. Okay, so we have this. These are DB, DA, and DB. Move freely, do the association. Okay, so here we can see that these are the, and here again we see that these are the first side and these are the second side. Okay, so the first side taking it 10, and second side if we take 1 times 10 to the power 8. Okay, so effect of this equation. So that is all for this associated kinetics for the molecular, okay, or the bimolecular association